The article likely made an error in referring to the worker as a journeyman and then later stating that he was unlicensed. In the electrical industry, a journeyman is a fully licensed electrician who has met certain requirements, including passing a licensing exam. It's unlikely that someone who is unlicensed would be referred to as a journeyman. The article states that the transformer was de-energized, which means that the electrical current had been turned off. However, it's still possible for a transformer to retain a residual charge even after being de-energized. This residual charge can be dangerous and can cause electrocution. There are a few possible explanations for how the worker may have been electrocuted. Firstly, improper grounding. If the transformer was not properly grounded, there may have been a path for electricity to flow through the worker's body. Secondly, residual charge is mentioned above. A transformer can retain a residual charge even after being de-energized. The worker may have come into contact with a conductor that was still carrying this residual charge. Thirdly, hidden energization. It's possible that the transformer was not actually de-energized, despite being labeled as such. This could have happened due to a faulty switch or other error. Without more information, it's difficult to say for certain how the worker was electrocuted. However, the above explanations provide some possible scenarios. It's important to note that working on electrical equipment, even when it's de-energized, can be extremely dangerous and should only be done by qualified and experienced personnel. Let's delve deeper into these potential causes of electrocution when working with seemingly de-energized transformers. Firstly, the importance of proper grounding cannot be overstated. Grounding provides a safe path for electrical current to flow in the event of a fault, preventing it from flowing through a person's body. According to the National Electrical Code, specifically NEC 250, grounding systems must be installed in accordance with specific requirements to ensure their effectiveness. This includes the use of appropriately sized grounding conductors, proper bonding of metal enclosures, and connection to a grounding electrode system. A common scenario in which improper grounding can lead to electrocution is when a transformer winding develops a fault and comes into contact with the metal enclosure. If the enclosure is not properly grounded, the entire enclosure can become energized, posing a significant shock hazard to anyone who touches it. This is why it's crucial to verify the integrity of the grounding system before working on or near any electrical equipment. Secondly, residual charge, also known as static electricity, can accumulate in a transformer's windings even after it has been disconnected from the power source. This is due to the capacitive nature of the windings, which can store electrical energy. While the amount of energy stored may not be large, it can still be enough to cause a painful shock or even electrocution under certain circumstances. To mitigate the risk of residual charge, it's essential to discharge the transformer windings using a suitable grounding device before commencing any work. This can be achieved by connecting a grounding rod to the transformer terminals, allowing any stored charge to safely dissipate to ground. The duration of the discharge process will depend on the size and design of the transformer, as well as the amount of residual charge present. Thirdly, hidden energization refers to the possibility that a transformer may still be energized despite being labeled as de-energized. This can occur due to a variety of factors, such as a faulty switch, incorrect wiring, or human error. For example, a switch may appear to be in the off position, but its contacts may be welded shut, allowing current to continue flowing to the transformer. Similarly, a wiring mistake could inadvertently create a backfeed, energizing the transformer from an alternate source. To prevent hidden energization, it's crucial to implement a robust lockout-tagout procedure before working on any electrical equipment. This involves physically disconnecting the power source, locking the disconnecting device in the off position, and attaching a tag indicating that the equipment is being worked on and should not be energized. Additionally, it's recommended to use a voltage tester to verify that the transformer is indeed de-energized before touching any of its components. In addition to these three primary causes, other factors can also contribute to the risk of electrocution when working with transformers. These include the presence of moisture, which can reduce the insulation resistance of electrical components, the use of improper tools or equipment, and inadequate training or supervision. To ensure electrical safety, it's essential to follow all applicable safety regulations and best practices, including those outlined in the National Electrical Code and other relevant standards. This includes wearing appropriate personal protective equipment, such as insulated gloves and safety glasses, using properly insulated tools, and maintaining a safe working distance from energized equipment. Furthermore, it's crucial to receive adequate training on the specific hazards associated with working on transformers and other electrical equipment. This training should cover topics such as lockout-tagout procedures, grounding techniques, and the proper use of voltage testers and other safety equipment. In conclusion, working on electrical equipment, even when it's de-energized, can be extremely dangerous and should only be done by qualified and experienced personnel who have received adequate training. By understanding the potential causes of electrocution and following all applicable safety regulations and best practices, it's possible to minimize the risk of electrical accidents and create a safer working environment. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations and safety. Several articles within the NEC are particularly relevant to working with transformers and ensuring electrical safety. NEC Article 450 covers transformers in detail, including requirements for insulation protection and grounding. This article addresses various aspects of transformer safety, such as overcurrent protection, ventilation, and clearances from combustible materials. It also specifies the requirements for transformer grounding, which is crucial for preventing electrical shock hazards. NEC Article 250, as previously mentioned, focuses on grounding and bonding. This article provides detailed requirements for grounding electrical systems and equipment, including transformers. It covers topics such as grounding electrode systems, equipment grounding conductors, and bonding of metal enclosures. Proper grounding is essential for providing a safe path for fault current to flow, minimizing the risk of electrical shock and fire. NEC Article 110 covers general requirements for electrical installations. This article includes provisions for working clearances around electrical equipment, guarding of live parts, and identification of disconnecting means. It also emphasizes the importance of qualified personnel performing electrical work and following safe work practices. NEC Article 70E, which is not strictly part of the NEC but is closely related, addresses electrical safety in the workplace. This standard provides guidance on hazard assessment, personal protective equipment, and safe work procedures for electrical work. It emphasizes the importance of creating an electrically safe work condition before commencing any work on electrical equipment. In addition to these NEC articles, other standards and regulations may also apply to working with transformers, depending on the specific application and location. These may include occupational safety and health administration, or OSHA regulations, as well as state and local electrical codes. It's important to be familiar with all applicable standards and regulations and to follow them diligently to ensure electrical safety. To further illustrate the importance of these concepts, let's consider a few real-world examples. In one case, a worker was electrocuted while working on a transformer that was supposedly de-energized. An investigation revealed that the transformer had not been properly grounded, and a fault in the windings had energized the metal enclosure. The worker came into contact with the energized enclosure and was electrocuted. This incident highlights the critical importance of proper grounding and the need to verify that equipment is truly de-energized before working on it. In another case, a worker was injured when he came into contact with a residual charge on a transformer. The worker had disconnected the transformer from the power source but had not discharged the windings. When he touched the terminal, he received a painful shock from the residual charge. This incident underscores the importance of discharging transformer windings before commencing any work. These examples demonstrate the potential consequences of neglecting electrical safety precautions. By understanding the hazards associated with working on transformers and following all applicable safety regulations and best practices, it's possible to prevent electrical accidents and protect workers from injury or death. Furthermore, it's important to foster a culture of safety in the workplace, where employees are encouraged to report hazards and ask questions without fear of reprisal. Regular safety training and toolbox talks can help reinforce safety awareness and ensure that workers are equipped with the knowledge and skills they need to work safely. In conclusion, electrical safety is paramount when working with transformers and other electrical equipment. By understanding the potential hazards, following all applicable safety regulations and best practices, and fostering a culture of safety in the workplace, it's possible to minimize the risk of electrical accidents and protect workers from harm. Remember, electricity is a powerful force that must be treated with respect. Always take the time to assess the risks, plan the work, and follow all safety procedures before commencing any electrical work. Never take shortcuts or compromise safety for the sake of expediency. Your life and the lives of your colleagues may depend on it. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer before performing any electrical work. They can provide specific guidance based on your individual circumstances and ensure that the work is performed safely and in accordance with all applicable codes and regulations. Stay safe and always prioritize electrical safety in everything you do. Now, let's get into specific scenarios and how the NEC addresses them to ensure safety when working with transformers. Consider a situation where a transformer is located in a damp or wet location. NEC 450.27 addresses transformers installed in these environments. It mandates that transformers in damp or wet locations must be identified for use in such locations or be provided with an enclosure suitable for the environment. This typically means using an NEMA 3R or NEMA 4 rated enclosure that protects the transformer from moisture ingress. Furthermore, the enclosure must be properly grounded to prevent shock hazards. Another scenario involves transformers installed indoors. NEC 450.21 specifies the requirements for transformer rooms or vaults. These rooms must be constructed of fire-resistant materials and have adequate ventilation to prevent overheating. The doors to these rooms must be marked with a warning sign indicating the presence of high-voltage equipment. Inside the room, there must be sufficient working space around the transformer to allow for safe maintenance and inspection. Overcurrent protection is another critical aspect of transformer safety. NEC 450.3 outlines the requirements for overcurrent protection of transformers. The primary and secondary sides of the transformer must be protected by fuses or circuit breakers that are sized appropriately for the transformer's rating. The overcurrent protection devices must be capable of interrupting the maximum fault current that could occur in the circuit. Furthermore, the overcurrent protection devices must be coordinated to prevent nuisance tripping. Grounding is essential for preventing electrical shock hazards when working with transformers. NEC 250 provides detailed requirements for grounding transformer systems. The transformer's neutral point must be grounded to provide a low impedance path for fault current to flow. The metal enclosure of the transformer must also be grounded to prevent it from becoming energized in the event of a fault. The grounding conductor must be sized appropriately for the transformer's rating and must be connected to a grounding electrode system. Lockout-tagout procedures are crucial for ensuring worker safety when working on de-energized transformers. OSHA Standard 1910.147 outlines the requirements for lockout-tagout. This standard requires employers to develop and implement a written lockout-tagout program that includes procedures for de-energizing equipment, applying locks and tags, and verifying that the equipment is de-energized. Workers must be trained on the lockout-tagout procedures and must follow them diligently. Personal protective equipment, or PPE, is essential for protecting workers from electrical hazards. The type of PPE required will depend on the specific task being performed and the potential hazards involved. Common types of PPE for electrical work include insulated gloves, safety glasses, and flame-resistant clothing. Insulated gloves must be rated for the voltage level of the equipment being worked on and must be inspected regularly for damage. Safety glasses must provide adequate protection from arc flash and flying debris. Flame-resistant clothing can protect workers from burns in the event of an arc flash. In addition to these specific scenarios, There are many other situations where the NEC and other standards provide guidance on transformer safety. It's important to be familiar with these standards and to follow them diligently to ensure a safe working environment. Remember, electrical safety is everyone's responsibility. By working together and following all applicable safety regulations and best practices, we can prevent electrical accidents and protect workers from harm. One more thing to consider is the arc flash hazard associated with transformers. An arc flash is a dangerous electrical explosion that can occur when a fault develops in an energized electrical circuit. Arc flashes can generate intense heat, pressure waves, and toxic gases, which can cause serious injuries or death. Transformers are a common source of arc flash hazards due to the high voltages and currents involved. To mitigate the arc flash hazard, it's important to conduct an arc flash hazard assessment before working on or near transformers. The assessment should determine the incident energy level at the work location and the required arc flash PPE. Arc flash PPE typically includes a face shield, arc-rated clothing, and insulated gloves. The incident energy level is a measure of the amount of energy released during an arc flash event. It is typically expressed in calories per square centimeter. The required arc flash PPE is determined by the incident energy level. For example, if the incident energy level is 4 calories per square centimeter, the worker would need to wear arc-rated clothing with an arc rating of at least 4 calories per square centimeter, as well as a face shield and insulated gloves. In addition to wearing arc flash PPE, it's important to follow safe work practices to minimize the risk of an arc flash. These practices include de-energizing equipment before working on it whenever possible, maintaining a safe working distance from energized equipment, and using insulated tools. It's also important to be aware of the potential causes of arc flashes and to take steps to prevent them. Common causes of arc flashes include accidental contact with energized conductors, insulation failure, and equipment malfunction. By following these precautions, it's possible to significantly reduce the risk of arc flash injuries when working with transformers. Another crucial element is regular maintenance and inspection of transformers. Consistent upkeep can identify potential issues before they escalate into hazardous situations. Inspections should include checking for signs of overheating, such as discolored insulation or bulging components, inspecting for leaks of oil or other fluids, verifying the tightness of connections, and testing the insulation resistance of windings. Over time, insulation can degrade due to heat, moisture, and other factors, increasing the risk of electrical faults. Routine testing can detect insulation weaknesses and allow for timely replacement of components. Maintenance should also include cleaning the transformer and its surroundings to remove dust, dirt, and other contaminants that can reduce cooling efficiency and increase the risk of fire. Additionally, ensure that ventilation openings are clear and unobstructed to allow for proper airflow. Keeping accurate records of maintenance and inspection activities is essential for tracking the condition of transformers and identifying any trends or patterns that may indicate potential problems. These records should include the date of the inspection, the name of the person who performed the inspection, the findings of the inspection, and any corrective actions taken. By implementing a comprehensive maintenance and inspection program, you can significantly extend the life of your transformers and improve their safety and reliability. This also helps to ensure compliance with applicable codes and regulations. Finally, consider the importance of communication and coordination among workers when performing electrical work. Effective communication is essential for ensuring that everyone is aware of the potential hazards and the steps being taken to mitigate them. Before starting any electrical work, hold a pre-job briefing to discuss the scope of the work, the potential hazards, and the safe work procedures to be followed. During the briefing, ensure that everyone understands their roles and responsibilities. Use clear and concise language and avoid using jargon or technical terms that may not be understood by everyone. Encourage workers to ask questions and voice any concerns they may have. Maintain open communication throughout the work process. If any changes occur or unexpected situations arise, communicate these changes immediately to everyone involved. Use hand signals or radios to communicate when verbal communication is not possible. Coordination is also essential for ensuring that multiple workers can work safely together. Designate a lead person to coordinate the work and to ensure that everyone is following the safe work procedures. Use a checklist to ensure that all steps are completed in the correct order. When working on de-energized equipment, verify that all workers have locked and tagged out the equipment before starting work. By prioritizing communication and coordination, you can create a safer working environment and prevent electrical accidents. Remember that electrical safety is a continuous process that requires ongoing effort and attention. By staying informed, following all applicable safety regulations and best practices, and fostering a culture of safety in the workplace, you can protect yourself and your colleagues from harm.